Hello, today we'll be talking about heaps. You'll be seeing a lot of animations in this video because I really think that visualizations can help you understand and remember concepts better. And then after you learn the basic concepts, you'll be able to write up a heap in code that can insert and extract data. And we'll be doing that from scratch with very beginner-friendly code in Go. I think heaps are a very interesting data structure because we think of it as a tree, but it's an array. So I think it's interesting to see how it works, especially when you're writing it up in code. The heap data structure was originally introduced as a part of an algorithm called heap sort. But the data structure that was introduced there was also useful for many other applications. Heaps are especially good for implementing priority queues. In normal queues, we take out the one that came in first, right? But in priority queues, we take out the one with the highest priority, which is where heaps can come in handy. A heap is a data structure that can be expressed as a complete tree. A complete tree means that all the levels in the tree are full, except for the lowest level, where some nodes can be empty, but have all its nodes to the left. We are looking at a binary heap here, where the nodes have up to 2 children. In the case for maxHeaps, the largest key will be stored in the root. And for all the nodes in the tree, every parent will have a higher key than its children. A maxHeap would be useful when we need to repeatedly remove a key that is the largest, because we already know that the largest key is in the root. This is a reason why getting the largest key can be so fast, regardless of the size of the heap. The opposite of the maxHeap is minHeap, where the root is the smallest key. So in a minHeap, each parent node will have the smaller key than its children. In this tutorial, we're just going to be talking about maxHeaps because minHeaps is just maxHeaps done opposite. Like we saw in the diagram so far, heaps can be visualized as a tree, but actually behind the scenes, the keys are stored as an array, where each node of the tree corresponds to an index of that array. So strictly speaking, heaps are actually just an array that operates like a tree. This is possible because you can just easily calculate the indices of the children based on the parent's index and vice versa. So with this simple formula, we can get the index of the children for any index of the heap. For example, if we want to get the left child node index of index number 39, 39 multiplied by 2 plus 1 will give us 79, which will be the index of the left child. Okay, so now that we know the structure of heaps, let's talk about the process of how we can insert keys in a heap. Whenever we do an insert, we're going to add the new key at the bottom to the right of the tree. In an array, the bottom right node will be the last index. After just mindlessly placing the new node there, we need to rearrange the nodes so that we can maintain the heap property, which is to keep the parent key larger than its children. We'll compare the new node to its parent node and swap it if the new node is higher. We follow up the tree and keep on repeating this process until it gets to its place. We call this process of rearranging the indices as Heapify. The Heapify process is also needed after taking out an item of the tree, so let's go and see how that works. To extract the highest key in a heap, we can just take out the root because we know that the root is the largest key. After that, we need to rearrange the nodes so that we can fill in the empty root while maintaining the heap property. So first step, right after losing the root, we will fill the empty root with the last node. So 34, which is the last key, will go to the root position. Then we'll start the swapping process starting from the top. Look at these 3 nodes at the top. Just think, out of the 3, who should be the parent? Like who should be on the top? It should be 50 because 50 is the largest out of the 3. So 50 becomes the parent by swapping positions with 34. In other words, the parent node 34 will be swapping places with its larger child. The same goes for the next round. 48 is the larger child, so we will be comparing 34 to 48. Is 34 larger than 48? No, so 34 doesn't deserve to stay there and it has to swap with 48. The time complexity of extracting and inserting a node in the heap would depend on the heapifying process. simply adding an element at the end of the array or taking out a key from the first index of the array would not be the dominant part of the time complexity. So we'll just ignore that part. However, the number of operations needed to heapify up or down would depend on how high the tree is. So that's going to be the one that affects the time complexity. So we can express insert and extract as O of h, where h means the height of the tree. If we want to express the time complexity with n, which would be the size of the array, we can just replace h with log of n because the height and the number of indices have a logarithmic relation. So the time complexity for inserting and extracting from a heap would be O of log n. You can see that the heapifying process is the tricky part. Just adding and taking out an element is easy, but rearranging the heap to maintain the heap property would be our main focus when we're doing the coding. We'll be doing three main things. First, we need to make a struct that represents maxHeap. Then we're going to write an insert method, and third, we're going to write an extract method. Insert and extract will be accessible from the outside. So insert and extract needs to start with a capital, and also the struct maxHeap should also start with a capital as well. So I'm just going to write them down here. And okay, so this is going to be the big structure for what we're going to write now. We're going to go and write down the struct for maxHeap. And maxHeap, it's only going to contain just like one slice. Okay, so it's actually a slice, but I'm just going to call it array. And then let's go to the insert part. So it's going to take in an integer, which is the key to add. And we'll be doing two things here. We're going to add the element to the array and then heapify. So adding the element should be... So we're just appending the new key that was passed in. And we're going to append that to the array. And then next we're going to rearrange it so that it can maintain the heap properties. This is the index of key because we appended it, and this is going to be the last index. And we didn't write this yet. That's going to be our next step. So it's going to take in an integer, indicating where the heapify is going to start. So inside the method, we want to say swap when the current index is larger than the parent. And to write that up, we need to write some supporting functions and methods. So we'll just write some functions that can help us convert the parent to the child indices, and also we need a method that can actually swap. So this is to get the parent. So the parent index can be expressed as index minus 1 divided by 2. The left child is always an odd number and the right child is always an even number. So it's just going to round down, and they're both going to indicate to the same parent index. So this is we're going to get the left child index, and this is going to be the parent, and we're going to return the left child index. And also the same goes for the right. And after that, we also need a method that can swap the two values of two indices. In this case, we actually have to modify the array. And it's going to take in two indices, and we're going to swap. Okay, so right now we're putting I2 into I1 and I1 into I2. And this expression, this actually works in Go. Okay, so now that we have these functions and methods, we can finally start to write the maxHeapify method. So when the parent is smaller than the current index, so this is the key of the parent and this is the key of the current index, and if the parent is smaller, then we're going to swap. And after we swap, we're going to perform the same loop on the parent, which is going to be the swapped key. So we need to update the loop. So right now, this part is swapping until it finds its place. And this part is updating the current index to its parent index so that we can loop again. We're not going to put an if statement actually stopping the loop, because if you look here, when index gets to 0, it's going to be impossible for this for condition to be satisfied, because the parent index and the index are both going to be 0. So the loop is just going to stop. So just for the sake of simplicity, I'm just going to leave it like this. And yeah, there was a little mistake here, sorry. Let's go to the main function now and test things out a little bit. Here. I'm going to make it into a slice. Just 10, 20, and 30. And I'm going to create a max heap. So I'm going to call that just M. Just to check the struct that we built. Okay, so you can see that inside the struct there is just one slice, which we call array, and that is currently empty right now. And then we're going to add some keys. And after each insert, let's just print out. Okay, so we're going to run here. First, we're going to insert 10. So it's just inserting as a root because there was nothing there. And after that, we insert 20, but you can see 20 is first added at the end, that it heapified and swap positions with 10, so that in the front, it's always the largest key at the front. And after that, we insert 30, and then we add it at the end, and then you can see it's swapped with 20, so that it can be, it's the biggest one, so that it can be at the front, at the root. Okay, so we just did a simple test. Let's go and do the next one, which is extract. So we have to return the item that we extracted. So before we make any changes to the max heap, let's just store it and just write the return part first. So we're storing the first index in extracted and returning it, and the rest of the process we'll write it between these two lines. So we're going to get the last key, the last index, and put it in the root, which would be the first index. So it's going to be So this part over here is going to be the last index, and we're putting that in index 0, the first index. Okay. And after we put the last index to the first index, we have to make the slice shorter, so that we can get rid of the last one. I have to write the last index here, which is already here. I don't want to be repeating myself, so I am going to write a variable, declare a variable that is, and replace that with nil. And also here I'm going to put nil. And then after that, I'm going to put the max Heapify down here. We didn't write the max Heapify down yet. I'm going to write it in the next step, but I'm just going to write it. And just one more step. If I extract from an empty array, it's going to panic. So just to prevent that, I'm going to say if the length of the array is 0, and then I'm just going to return that. So if it meets a return, it's just going to come out of the whole method. Okay. Inside this method, we first need to get the larger child, compare it to the current index, and then swap it. And we're going to repeat this loop until the index has no children. So first, let's write a for loop. So imagine there is an index with only one child, and that only child would be the last index because it's a nearly complete tree. So if the left child index is the same as or smaller than the last index of the array, we can say that this index has at least one child. So here we want to say left child is same as or smaller than the last index. Child to compare is going to be the child to compare with the index and to swap. And now I can say L, which is left index, is smaller or same as the last index. So I'm going to make a for loop. And first thing we need to do is to define the child to compare. When there is only one child, or if the left child is larger, we're going to assign the left child as child to compare. So when I index is the only child, or okay, so for these two cases, when the index is the left child, so when the left child is the only child, or when the left child is larger than the right child, we're going to put L as child to compare, and in this case we're going to put R as child to compare. Okay, so we put L as child to compare for these two conditions, and when the right child is larger, I just put it else. R is going to be child to compare. Just make sure to put this part at the first of the if statement, because if this is true, we don't want to be accessing the right child. So because there's no right child and it's just going to cause a panic. So just make sure you have this. If this is actually true, it's going to skip the rest. Okay, so we've finished deciding the index for child to compare. Now let's go and compare and do the swapping. So if the value of the array for index is smaller than child to compare, so if it's smaller, then we're going to do the swapping. And after we swap, we need to update variables in the loop so that the next round we will be doing this on the swapped index. So this is when actually the index is smaller than the child to compare and we swap. But if else, if the value of the current index is actually larger than the larger child, that means that it has found its right place. So we will stop the whole Heapify process and we're going to return like that. Okay, so this is it. Let's go and test this out. So we're going to go to the main function, sorry. So I'm going to add a little bit more to the heap. So I'm going to add and then I'm going to go and extract 5 times. So I need a for loop for that. Okay, just run the process. And you can see that it's inserting, and then starting from here, we're going to be extracting. And the largest key is always in the front. So when we're doing the extracting, I am actually going to go and see if we can put a breakpoint and actually observe the swapping process. So I'm going to go to maxHeapify Down, and whenever we have a swap, I want to see it. So I'm going to put a breakpoint here. Then I'm going to go to debug, and I'm going to debug it. And it's a bit big. I'm just going to make it a bit smaller. So right now we stopped here. So inside H, this is the address and this is the actual heap. And inside the heap, there's an array. And inside the array, there are the keys. Before 30 was at the front, but because we went through that process of putting the last key to the front, 7, which was at the last, has already come to the front. And if we run again, 7 has exchanged its place with 20 because it doesn't deserve to belong there. It's too small. So it exchanged. And then you can see that the index here is always going to follow the index of 7, which is the key that used to be at the back. And run again. And you see that 11 has swapped places with 7 here. Run again. So this time 10 has come forward and it already swapped places with 17. And then it's going to swap with 15. And then the next 5 came to the front and then it exchanged with 15, and it just goes on and on. Swap again with 13. Okay, so this is how you can observe the process of the swapping. Okay, so that's it for today. If you want to see more of my videos, please subscribe to this channel. I hope you had fun learning about heaps. Thank you so much for watching, especially to those who has been watching until the end. I'll see you on the next video. Thank you so much. Bye bye.